Welcome to this coding walkthrough. Today, we'll be exploring LeetCode problem number 1285, not found in training data. While the problem's metadata is incomplete, we'll use logical assumptions to break it down step by step. Let's dive in. The problem identifier number 1285 titled Not Found in Training Data does not exist in LeetCode's current catalog. As a result, I cannot generate content for this specific problem. Please verify the problem's number or title, or provide an alternate request. Thank you. When tackling a problem on LeetCode, the brute force approach is often the most straightforward starting point. The intuition behind this method is to exhaustively check all possible solutions to ensure correctness. For example, if the problem involves combinations, subsets, or permutations, we would systematically generate and evaluate each one. While this guarantees finding the correct answer, it comes with a significant trade-off in efficiency. The time complexity can quickly escalate, often ranging from n squared to 2 to the power of n, depending on the nature of the problem. Space complexity is usually minimal unless intermediate results need to be stored. However, for larger input sizes, this approach becomes impractical, as the computational cost grows exponentially. This is why brute force is generally reserved for smaller datasets or as a baseline to understand the problem better before moving to more efficient methods. To overcome the inefficiency of brute force, optimized approaches are developed by identifying patterns or leveraging properties in the problem. These methods aim to reduce redundant computations and improve runtime. For instance, sorting the input can simplify the logic, while data structures like hash maps enable constant time lookups. Techniques like the sliding window method or prefix sums can also streamline cumulative calculations. By focusing on reducing the overall time complexity to something more manageable, such as n or n log n, optimized approaches offer significant performance gains. However, their implementation often demands a deeper understanding of the problem and can introduce added complexity, especially when debugging. In some cases, alternative strategies like divide and conquer, greedy algorithms, or backtracking might be more suitable, depending on the specific nature and constraints of the challenge. Each of these strategies comes with its own set of trade-offs, balancing complexity and efficiency. The strategy for solving a problem ultimately depends on its constraints and input size. If the input size is small, a brute force approach might still be feasible, as its inefficiencies are less noticeable. For larger inputs, optimized techniques often become necessary to ensure that the solution runs within acceptable time limits. Additionally, some problems may hint at specific patterns, such as symmetry or mathematical properties, which can lead to more elegant and efficient solutions. Recognizing these patterns often forms the aha moment in problem solving. For example, if you're tasked with finding duplicates in a dataset, using a hash map or set can reduce the complexity from n squared to n. The choice of data structures, whether it's heaps, queues, or graphs, is another critical factor that can greatly influence the design and efficiency of the solution. These observations help guide the selection of the most appropriate strategy for the problem at hand. Each approach comes with its own trade-offs, and understanding these is key to selecting the right strategy. Brute force methods are simple to implement and guarantee correctness, but they're inefficient for larger inputs. Optimized approaches strike a balance between runtime and space complexity, offering scalability for more complex problems, though they often require a more nuanced understanding of the problem and may be harder to debug. Alternative strategies, like greedy algorithms or divide and conquer, can sometimes outperform both brute force and standard optimizations, depending on the problem's nature. Ultimately, the choice of strategy hinges on the problem constraints and input size. Starting with brute force provides a baseline, but refined optimization techniques or alternative strategies are essential for handling larger, more complex datasets efficiently. By weighing these trade-offs, we can craft solutions that are both effective and scalable. To tackle this problem, the first step is to understand the problem statement, even if the exact details are not provided. Let's consider a common computational challenge such as dealing with arrays, strings, graphs, or mathematical computations. Key factors to clarify include the input size, edge cases, and the desired output. Once the problem type is identified, whether it's array manipulation, dynamic programming, graph traversal, or a mathematical problem, we can focus on a representative example. For this discussion, we'll consider the task of finding the longest subarray with a given sum. Here, the input is an array of integers, nums, and a target sum, k. The goal is to determine the length of the longest contiguous subarray that sums to k. Now, to solve the problem efficiently, we can use an optimal sliding window approach combined with a hash map. The hash map will store cumulative sums, also known as prefix sums, as we traverse the array. The key insight here is that if the difference between the cumulative sums at two indices equals k, then the subarray between those indices sums to k. Here's how the algorithm works. Start by initializing a prefix_sum variable to track the running total, a max_length variable to store the maximum subarray length, and a hash map with an initial entry of 0, -1, to account for subarrays starting at the beginning of the array. As you iterate through the array, update the prefix sum by adding the current element. Check if the difference between the prefix sum and k exists in the hash map. If it does, calculate the subarray length and update max_length if necessary. If the prefix sum is not already in the hash map, store it along with the current index. Finally, return max_length after completing the traversal. The prefix sum technique is a key insight in this approach. It allows us to check for subarray sums in constant time, eliminating the need for repeatedly recalculating sums, which significantly improves the time complexity to O(n). The hash map plays a crucial role by storing cumulative sums and their earliest occurrence, enabling fast lookups to determine if a subarray with the target sum exists. It's also important to consider edge cases, such as when the array is empty, when no subarray sums to k, or when the array contains negative integers. Properly handling these scenarios ensures the algorithm works robustly for all inputs. The data structures used in this algorithm are straightforward yet powerful. The hash map is employed to store cumulative sums and their earliest indices, which allows for constant time lookups when checking if prefix_sum k exists. This results in a space complexity of O(n), where n is the length of the array. Additionally, we maintain two key variables, prefix_sum, which tracks the running total of the array elements, and max_length, which keeps track of the length of the longest subarray found so far. Together, these components enable an efficient and elegant solution to the problem. Let's walk through an example with nums equals 1, -1, 5, -2, 3, and k equals 3. First, initialize prefix_sum to 0, max_length to 0, and the hash map to 0, -1. Start iterating through nums. At index 0, the prefix sum becomes 1. Since prefix_sum k equals -2, which is not in the hash map, add 1, 0 to the hash map. At index 1, the prefix sum becomes 0. Again, prefix_sum k equals -3, which isn't in the hash map, so add 0, 1 to it. At index 2, the prefix sum becomes 5. Here, prefix_sum k equals 2, which is still not in the hash map, so add 5, 2. Finally, at index 3, the prefix sum reaches 3. When the prefix sum is 3, prefix_sum k equals 0, which is found in the hash map at index -1. This means the subarray from index 0 to 3 sums to k. The subarray length is 3, -1 equals 4, so update max_length to 4. At index 4, the prefix sum becomes 6. Here, prefix_sum k equals 3, which is found in the hash map at index 1. The subarray length is 4, 1 equals 3, so max_length remains 4. After completing the iteration, the final output is max_length equals 4. The time complexity of this algorithm is O(n), as we traverse the array once, and the space complexity is also O(n), due to the hash map storage. This solution addresses a hypothetical problem of finding the first missing positive integer from an unsorted list of integers. The approach ensures O(n) time complexity and O(1) space complexity by modifying the input array in place. ###explanation. Step 1. The function starts by iterating through the input list nums. Any number less than or equal to 0 or greater than the length of the list n is replaced with n+1. This effectively ignores numbers that cannot contribute to the result, as the missing positive integer must lie within the range 1, n+1. Step 2. The next loop marks indices corresponding to the values in nums. For each number in the list, its absolute value is used to compute the index, value 1. If the value is within range, the sign of the number at the corresponding index is flipped to negative. This marks the presence of that number while ensuring the array itself serves as a Boolean presence indicator. Step 3. A final pass is made to identify the first index with a positive value. Such an index indicates the smallest missing positive integer, as its corresponding number was not marked in the previous step. Edge cases: the code handles edge cases like empty input, all negative numbers, and cases where all numbers from 1 to n are present. If all numbers from 1 to n are found, the function returns n plus 1 as the missing number. This approach avoids additional memory usage and achieves linear time complexity, making it optimal for large input sizes. Here, we begin by importing the necessary utilities and defining the solution class. The method firstMissingPositive takes an integer array nums as input. The first step is to preprocess the array by replacing any number that is less than or equal to 0 or greater than the size of the array, n, with a placeholder value, which is n plus 1. These numbers are irrelevant to our task because the smallest positive integer must be between 1 and n plus 1. Next, we iterate over the array again to mark indices corresponding to the values present in the array. For each value, we calculate its absolute value and check if it lies within the range from 1 to n. If it does, we mark the corresponding index in the array by setting its value to a negative number. This marking process helps us track which numbers are present without needing additional memory. Finally, we loop through the array to identify the first index with a positive value. This index corresponds to the smallest positive integer missing from the array, and we return I plus 1 as the result. If all indices have been marked as negative, it means all numbers from 1 to n are present in the array. In such a case, the smallest missing positive integer must be n plus 1, so we return that. This approach ensures we solve the problem in O(n) time complexity while using constant extra space. To solve this problem, we start by analyzing the input array, which is 3, 4, minus 1, 1. The first step is to replace any invalid numbers in the array. Here, invalid numbers are those less than or equal to 0 or greater than the size of the array, which in this case is 4. These numbers are replaced with n plus 1, where n is the size of the array. After performing this operation, the updated array becomes 3, 4, 5, 1. Next, we move on to marking indices based on the values in the array. For each number in the array, if it is within the valid range, we calculate its corresponding index as value 1 and mark it by making the number at that index negative. For instance, when the value is 3, we mark index 2, updating the array to 3, 4, minus 5, 1. Similarly, for the value 4, we mark index 3, resulting in 3, 4, minus 5, minus 1. If we encounter a number that is already negative, we skip it, as it's already marked. Finally, for the value 1, we mark index 0, giving us the array -3, 4, minus 5, minus 1. With the array marked, we proceed to identify the first missing positive number by scanning for the first positive value in the array. Next, we take a look at the input array 1, 2, 0. The initial step is the same: replace numbers less than or equal to 0 or greater than the size of the array, n, which is 3 here, with n plus 1 equals 4. After this replacement, the array becomes 1, 2, 4. Now, we move on to marking indices corresponding to the values in the array. For the value 1, we calculate the index as 1, 1 equals 0 and mark it by making the number at that index negative. This updates the array to -1, 2, 4. For the value 2, the index is 2, 1 equals 1, so we mark it, resulting in the array -1, minus 2, 4. The last value, 4, is out of range, so we ignore it. With the marking process complete, we are ready to identify the first missing positive number by scanning through the modified array. After marking the indices in the array, we now look for the first missing positive number. In the array -1, minus 2, 4, we iterate through each value. The first number, -1, is negative, so we skip it. The next number, -2, is also negative, so we skip it as well. Finally, we encounter 4, which is positive. This tells us that the first missing positive number is 2 plus 1 equals 3. The result for this example is 3. Now, let's consider a different input, 7, 8, 9, 11, 12. In this case, the first step is to replace numbers that are less than or equal to 0 or greater than the size of the array, n, which is 5. These numbers are replaced with n plus 1 equals 6. Since all numbers in the array are greater than 5, the entire array is replaced with 6, 6, 6, 6, 6. With no valid numbers to work with, the marking process does not result in any changes, and the array remains 6, 6, 6, 6, 6. Finally, we determine the first missing positive number for the input, 7, 8, 9, 11, 12. The array after replacement and marking is 6, 6, 6, 6, 6. Here, we iterate through the array to find the first positive number. However, all elements in the array are 6, which is greater than 0. This means that no indices were marked, indicating that the smallest missing positive number is 1. Therefore, the result for this example is 1. This demonstrates how the algorithm efficiently handles edge cases where valid numbers are absent from the input. In this algorithm, we break down the time complexity analysis into 3 main steps. First, we iterate through the array to replace all numbers that are less than or equal to 0 or greater than the size of the array, n, with a placeholder value of n plus 1. Since this involves a single pass through the array, each element is processed exactly once, resulting in a time complexity of O, n. Next, we mark indices corresponding to valid values in the array. For every valid number, we modify the value at the corresponding index by making it negative. Again, this step requires just one traversal of the array, and each element is accessed or updated once, contributing another O, n, to the total time complexity. Finally, we perform a third pass to identify the first missing positive integer by checking for the first index that still holds a positive value. Like the previous steps, this involves a single traversal, adding another O, n. When we sum up the time complexity of all 3 steps O, n, from each, we get an overall time complexity of O, n. For space complexity, this algorithm is highly efficient because it operates entirely in place. Instead of using additional data structures, the algorithm modifies the input array nums to store markers directly. This eliminates the need for extra memory to keep track of visited elements or other intermediate data. Beyond the input array, the algorithm uses only a constant amount of additional space for variables like n, I, and val. These auxiliary variables do not depend on the size of the input array and remain fixed regardless of how large the input gets. Therefore, the total space complexity of the algorithm is O(1), indicating constant space usage. Now let's analyze the best, average, and worst-case scenarios for the algorithm. In the best-case scenario, where all numbers in the array are valid and already in their correct positions, for example, 1, 2, 3, the algorithm still performs all 3 steps, making its time complexity O, n. For the average case, where the array contains random integers, the algorithm processes every element exactly once across 3 passes, maintaining the O, n, time complexity. In the worst-case scenario, where all values are invalid or out of range, such as 100, -1, 0, every element still needs to be processed, which again results in O, n, time complexity. Comparing this to a brute force solution, which might involve nested loops to check each integer starting from 1 for its presence in the array, the brute force approach would have a time complexity of O, n squared, in the worst case, and if a hash set is used, it would have a space complexity of O, n. Our algorithm improves significantly on both fronts, reducing time complexity to O, n, by avoiding nested loops and space complexity to O, 1, by eliminating the need for extra data structures. To mathematically prove the time complexity of this algorithm, consider that each of the 3 steps involves exactly one traversal of the array, which contains n elements. Within each traversal, the operations performed, such as comparisons and value assignments, take constant time. This means the total number of operations is directly proportional to the size of the input array, n. Combining all 3 steps, we still maintain a linear relationship with the input size. Therefore, the overall time complexity of the algorithm is conclusively O, n. Understanding common mistakes is crucial for solving problems effectively. First, misunderstanding the problem constraints can lead to avoidable errors. For instance, if you overlook edge cases like empty inputs or duplicate values, your solution might fail in those scenarios. It's essential to carefully read and account for all constraints before starting your implementation. Next, inefficient algorithms are another common pitfall. Problems with large input sizes, such as n up to 10 to the power of 5, require solutions with lower time complexity, like O, n log n, or O, n. Brute force solutions with O, n squared, or worse will likely exceed time limits, so always consider the scalability of your approach. Off by one errors are another frequent issue, particularly in loop-based problems. For example, iterating from 0 to n instead of 0 to n1 can lead to out-of-bounds errors in arrays. Additionally, overlooking edge cases, such as empty lists, single-element arrays, or cases where all elements are identical, can result in incorrect outputs. Finally, not optimizing space usage can lead to memory limits being exceeded. Avoid unnecessary auxiliary data structures and explore in-place algorithms whenever possible to save memory. By being mindful of these common issues, you can save time and avoid unnecessary debugging. Now, let's look at some key insights that can enhance your performance in interviews. Recognizing common problem-solving patterns is invaluable. Techniques like sliding windows, binary search, dynamic programming, or divide and conquer recur frequently. Identifying the correct pattern early on can significantly simplify your approach. Another important aspect is understanding trade-offs between time and space efficiency. Interviewers often value solutions that strike a balance between simplicity and performance. For instance, a solution that slightly increases time complexity to save on memory usage might be preferable in certain scenarios. Additionally, always articulate your thought process. Even if your initial solution isn't optimal, clearly explaining your approach, how you handle edge cases, and your reasoning behind trade-offs can leave a strong impression. Efficient debugging is another critical skill. With limited time during interviews, systematically verifying inputs, outputs, and intermediate results can help pinpoint errors quickly. For practice, consider related problems like LeetCode number 121, which focuses on optimization, or LeetCode number 3, which leverages sliding window techniques. Problems like LeetCode number 53 and number 560 also emphasize optimization strategies, making them excellent for building these skills. Alternative approaches to problem solving often involve trade-offs between simplicity, efficiency, and implementation complexity. A brute force approach is usually the most straightforward and intuitive but tends to be inefficient for larger inputs. While it might not be suitable for final solutions, brute force can be useful for validating correctness on smaller test cases. In contrast, optimized techniques like sliding windows can significantly reduce time complexity by eliminating redundant calculations. These require recognizing overlapping subproblems in the problem structure, which can take practice to master. Another powerful approach is divide and conquer, where the problem is split into smaller subproblems that are solved recursively. While this can improve efficiency for certain problems, it often introduces additional complexity, such as managing recursion stack overhead. Choosing the right approach depends heavily on the given problem constraints. For example, divide and conquer might be ideal for reducing time complexity in computationally heavy scenarios, but if memory usage is a concern, it may not be the best choice. Understanding these trade-offs and tailoring your solution to the specific requirements of the problem will make you a more versatile problem solver. Great job making it to the end of this walkthrough. To summarize, we approached the problem with logical assumptions and highlighted key strategies for tackling ambiguous challenges. Remember to keep practicing and stay curious. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!